We're going to start you off with a little phased array. So our office has had a UT program for many years, ever since I've started working there, probably about 25 years ago, doing conventional UT. I've got a fair amount of UT experience in my career, mostly on mechanical components. But this is our very first experience using phased array. This is our first project we've ever used it on, so we're pretty new to this technology. We're still in the steep part of the learning curve on this stuff. And so anyway, we've considered going to a phased array in the past before, but it was just too expensive. We couldn't justify it. The machines were very complex. They're big and bulky, and not really suitable for our purposes. So, but recently, most manufacturers have come out with what I call entry-level machines. They're more suitable for our applications. They're smaller, lighter, more portable. They're simpler to use, and most of all, they're cheaper. So these were more appropriate for our applications. So we decided to go ahead. We purchased an OmniScan SX. This is their entry-level machine. It lacks some of the features of the higher-end machines, but it's still a very powerful and capable machine. One of the good things about these, they also do conventional UT, so you can switch back and forth between the two, so that's pretty convenient. For those of you who aren't familiar with phased array, I'd like to go over quickly some of the basics, just so you understand the terminology and that sort of thing. So basically the principle behind phased array is you're able to electronically steer the beam as opposed to conventional UT where the beam is fixed. This allows a lot of flexibility in this method. So the probe that we use has multiple elements. They're arranged in an array. The element pulses are delayed or phased from each other, and the wavelets generated by each element form into a single wavefront, and the direction of travel of that wavefront is dictated by the phasing delay. So a focal law is basically all the instructions and the formulas and the parameters used to generate a beam at a specific angle. So each beam that it generates requires a focal law, and each beam results in a separate A-scan. And the A-scan is the typical display that you see when you're doing conventional UT. So you can generate a beam set with multiple focal laws. This is also referred to as a group. In this example, we're scanning between minus 30 degrees and plus 30 degrees in 2-degree increments. It requires 30 focal laws to do this, and generates 30 separate A-scans from that group. So some of the advantages of phased array versus conventional UT, you get better coverage from a single probe position. That kind of leads into the rest of these advantages. Requires less probe movement, less sensitive to probe position and user variability, increased probability of detection, more consistent and repeatable, easier interpretation of results, and better documentation and reporting. I kind of like this one down here, more visual. You know, I'm the kind that when I read a magazine, I just look at the pictures, you know, so I like pictures. And this gives you a more visual representation of what's going on. So some of the disadvantages, the higher costs. It's still, even though these machines cost about half what the higher end machines cost, they're still, compared to conventional UT, pretty expensive. They're more complex, more training requirements, not quite as portable as conventional UT, and less depth of penetration. I kind of use the analogy of a floodlight versus a spotlight. So these disadvantages, the gap is narrowing with conventional UT as the technology improves. So what are we going to use phased array for? We don't use it for weld inspections. We don't inspect welds with UT on in-service bridges typically. Most of the weld inspections are visual or occasionally mag particle or dye penetrant. Probably 80 to 90% of the people that use phased array use it for weld inspections, but we're a little different. So we mainly use it on cylindrical components, pins, bolts, shafts, and trunnions. Phased array is not intended to replace our conventional UT program. Conventional UT is still the go-to method for production work. Mainly we reserve phased array for things that require more in-depth evaluations or better characterization of known indications, things that are ultrasonically complex, that have a lot of reflectors that really clutter up the A scans. Phased array has some advantages there. And if we need better documentation or monitoring, we'd go to phased array. So soon after we purchased our SX, along comes Northport Bridge. It's a cantilevered through truss built in 1948, crosses the Columbia River. It's located up in the northeast part of the state, a very beautiful scenic part of the state, very remote. It's about as far away from our office as you can get without leaving the state, about 5 miles from the Canadian border. The distance kind of created some issues with trying out new technology. We had to do a lot of MacGyvering and that sort of thing. So. This is the bridge. The overall span length is 840 feet. It's got a drop-in span of 224 feet and anchor span of 168 feet. This is one of the tension links at the back span of the anchor span. These are considered fracture critical. They're in tension from both dead. Oh, I forgot. I'm not supposed to say that. These are in tension for both dead load and live load. They never go into compression, even under live load on this bridge. They are anchored to the piers with 6 anchor bolts at each link. The anchor bolts are not considered fracture critical because of the redundancy. And this kind of folds into what was said the other day about getting locked into terminology. The focus of the fracture critical inspections is on the link and the pins, but really the real problem here lurks down below in the non-fracture critical members. The bolts are threaded on the top 6 inches with 2 3/4 diameter threads. The bodies are 2 1/4 inch diameter. The lengths are 25 feet long at one pier, 12 feet long on the other pier, and the depth or the distance from the top of the bolts to the top of the concrete varies from 15 to 18 inches. So in 2013, routine inspections found these bolts were buried under debris. The debris was removed, and they observed a lot of section loss in the bolts because the debris was holding moisture up against the bolts. So they measured the section loss, did a structural analysis, and found that the bolts were still adequate. So a repair was issued to clean these things up and paint them, protect them from future degradation. So come back in 2016, you can see that they're not holding up very well. This is mainly due because of those stiffeners on the sides really restricted access around to the back side of these bolts, and you really couldn't get a good cleaning and painting job on the back side. So in 2016, they found further degradation of the bolts, further section loss and laminar corrosion. So in-depth inspection was in order on these. The objective is to measure the remaining sections, calculate the remaining capacities, and detect any stress corrosion cracking. So we did use different methods to inspect these bolts on the exposed sections. We used visual inspections, and it was difficult to get to the back sides to even look at those. We did some side scans with conventional UT along the face of the bolts to measure the remaining diameters in the exposed section. And then down below on the concealed sections, we didn't really have a good method for measuring section loss down below where we can't see and we can't get our hands on. So we did a little research, and we found that others were using phased array to do this type work. We already had a phased array equipment, so we decided that we would go this route. In fact, there's a commercial product out there available that is built specifically for scanning bolts with phased array. So what did we find with the visual inspections? It was very wet with a lot of debris accumulation around the anchors. This was caused by ineffective drains and gutters. These things were poorly designed and they just clogged up too fast. You can see up above that there is a finger joint up above, lets a lot of stuff fall down in there. The drains just weren't adequate enough to handle everything, and everything flowed out onto the piers and around the anchors. So we did some side scans with conventional UT to measure the remaining diameters of the bolts. We used a 1/2 inch diameter 5 megahertz transducer. This was limited to the exposed sections and shooting from front of the bolt to the back of the bolt. We couldn't get side to side because the probe just physically wouldn't fit in there. These are the results of those scans. The original diameter was 2¼ inches. The worst bolt we found had 1¼ remaining diameter at NW2, and then the best bolt was Southwest 3 at 2.11 inches. So this data was taken, another structural analysis was done, and found that the bolts were now inadequate. So immediate restrictions were placed on the bridge. It was restricted to 1 lane. Speed limit was dropped to 10 miles an hour. We placed concrete barrier sections on the back side of the anchor span to reduce the tension in the anchors. And then weight was limited to legal loads only. So on the concealed areas, like I said, we decided to go with encoded phased array using a bolt scanner by Eclipse Scientific. You can see in that photograph that the holes in the bottom of the pedestal are oversized and that there's a gap there, and that debris and moisture can get trapped in there. So we were concerned about those areas. We wanted to get a handle on what was going on there. This is the bolt scanner made by Eclipse Scientific. It basically clamps onto the top of the bolt. The probe is held against the top with spring force, and that top portion rotates around, so it allows you to rotate the probe in a controlled manner. It also has a wheeled encoder that allows us to record the probe rotational position along with the ultrasound data. Before we started scanning the Northport bolts, we made a couple test bolts we could practice on. Test bolt 1 had 4 notches in it, 2 in the threads, 1 in the transition, and 1 in the body. Test bolt 2 we left blank for now. We developed 3 scan groups to look at these bolts. Group 1 focused mainly on the thread area. We're scanning between 0 and 30 degrees in 1 degree increments, range of 0 to 6 inches. Group 2, we're looking mainly in the transition area where it necks down. We scan between 0 and 15 degrees in half-degree increments in a range of 4 to 8 inches. And then the last group, we're basically looking at the whole bolt. We're looking from -19 to +19 degrees in 1 degree increments and a range of 1 to 21 inches. So group 3 was the most useful group to me. This is the one that I'm going to focus on during the presentation. I could see everything that I needed to see in this group, and if I needed to look at something in more detail, I could go back to the group 1 or group 2. The UT machine that we bought, the SX, to do these 3 different groups, you have to do 3 different scans. On the higher end units, you could do all 3 of these in 1 scan. So that's one of the downsides of the entry-level machines. You'll note in each one of these that the probe is offset from center. We did that intentionally so we could get different angles of attack onto from the front side of the probe to the back side of the probe. And I'll show you how that benefited us here in a minute. So the idea of group 3 was that we would pick up thread indications on both sides of the bolt simultaneously, and then we could use those indications to establish the geometry of the bolt, and from there we could measure distance from indications from the surface of the bolt. This is a typical layout that we used. The SX has a lot of different layout configurations that you can use. This is the one that works good for us. Up here in the upper left is the A scan. This is the typical view you see in conventional UT. It's got sound path or depth along the x-axis and amplitude along the y-axis. This is the scan that all the other scans are built from. So this is the basic building block that makes up the other scans. Over on the upper right is the S scan, or the sectoral scan. This is basically a section through the part in the orientation of the probe at the location of the probe. It has width across the bolt on the x-axis and depth across the bolt on the y-axis. Amplitude is represented by colors according to the color palette shown on the right. So in this case, we're scanning between -19 to +19 degrees. The negative angles are on the left side of the S scan, and the positive angles are on the right side. So to make this S scan, it takes 39 focal laws, and it results in 39 different A scans. The data cursor that I've highlighted right here is the is the current focal law that's shown in the A scan to the left. So down below is the C scan, and the C scan is a little bit harder to visualize what it actually is, but I'll do my best here to try to explain it to you. Across the x-axis is probe rotational position from 0 to 360 degrees, and we're going in 1 degree increments. On the y-axis, we have the beam angle or focal law between minus 19 and plus 19 degrees. And then again, amplitude is represented by color. So I positioned the probe cursor at a particular angle. So this probe is located at that position where that yellow spot in the middle is. That probe position is represented by the S scan shown up in the upper right. So there are 360 different S scans that make up that C scan. The horizontal cursor is the same thing as the data cursor up in the S scan, shows the current focal law. And the intersection of those two cursors shows the A scan that applies to that point in the C scan. So there are 14,040 A scans that make up that C scan. So you can see that C scan contains a lot of information. It basically gives you a picture of the whole bolt. So to help you visualize what a C scan is, I take this example of a flat plate with a butt weld. We are taking the probe. The probe is scanning in this direction, and it's being moved in this direction here. So the C scan in this case is basically a top view looking down on the part. And it's a little different in our case where we're rotating the probe instead of moving it in a line, but it's basically the same principle. It's a little harder to visualize though. So this is a scan for test bolt 1 using group 3. You can see I put the cursors over here on the thread indications up at the top, and the width between those cursors was measured 2.45 inches. That's very close to the minor diameter of the threads, which is 2.45 inches. So it's pretty accurate. I then moved the cursors in equal amounts to equal the theoretical diameter of the bolt. And now those cursors represent the body of the bolt, or approximate it. If you look down in the C scan, this band across the middle of the C scan, I show the equivalent area up on the S scan. So we're basically looking at the body of the bolt below the threads in that zone. So if the bolt was completely free of defects, that area would be clear blue skies down there. The band across the top represents the threads on the positive side of the probe, and then the negative side over here. So I've positioned my probe on that indication that we in the body of the bolt on the C scan, and the data cursor up in the S scan. And what you can see over in the A scan, this is our notch down there at 14.9 inches. You can see it up here. The indication right above that is my notch in the transition, and the indication right above that is my notch in the threads. I only get one of the notches in the threads because my scan angle doesn't hit the one up top. But if you note the amplitudes of these indications and compare them to when we rotate the probe around, well, here first let me show this. Here I've overlaid the S scan on a CAD drawing of the bolt, and you can see how these notch indications show up. So then I rotate my probe 180 degrees, so the back side of the probe, or the negative angles, are hitting those same notches. So now my probe is over here, and you can see this little dark spot right here is my notch down there in the body of the bolt, 14.9 inches. It shows up right here on the S scan, and it shows up here on the A scan, and you'll note that the amplitude of that is quite a bit less. The opposite is true for the notches up in the threads. The amplitude was quite a bit higher when we hit it with the back side of the probe than the front side. So that was important to note, that when we're looking for things in the body, we're trying to look at the positive angles. When we're looking for things in the thread, we're looking at the negative angles. So here's another drawing of the notches shown on a CAD drawing. You can see how they're positioned. So this is test bolt 2, the one that we intentionally left blank. My intention here was to get a clean scan and then show you what a clean scan was, and then we would add some corrosion type indications to it. But when I scanned it, this should be clear blue skies down here in the center band, but you can see we got a lot of clouds in there. It turned out that this bolt had an inclusion or something about 8 inches down that kind of messed us up there, so that didn't work out as we planned. So before we could scan the bolts at Northport, we had to do a lot of prep to the tops of the bolts so the clamp would fit. Maintenance was generous enough for us to go out there and do this, and they did a lot of work out there cutting and grinding the tops of the bolts. You'll notice the can of WD-40 over there. You're wondering what we're using WD-40 for UT work? Steve Littlejohn shaking his head back there. So the first day that we went out and did our scans, it was pretty cold. It was about 10 degrees out, and I pulled out my bottle of couplant gel and squeezed it onto the top of the bolt, and it just froze instantly. So apparently we didn't have low temperature couplant. So we're out in the middle of nowhere. It's pretty remote out there. So I'm looking through my truck to what I can use as a substitute, and I grabbed that can of WD-40, and it worked really well, so we ended up using that for the rest of the scans, even when it wasn't freezing. So there are 24 tension anchor bolts total. Each bolt was scanned at least 6 times, twice for each group. We did 198 scans total in 3 days. This is kind of a typical result. This is bolt NW5. You can see that band representing the body of the bolt down the middle has some clouds in it. That's the corrosion that we're looking for. I've got the cursors up in the S scan representing the diameter of the bolt, and you can see some stuff on the positive side of the transducer that's showing up along the side of the bolt. And this is kind of where we're not real satisfied with this method so far. We were hoping to get better imaging of the profile of the side of that bolt. But the good news is that this was our first try at this, so we got a lot of room to improve. I think there's a lot of things that we can change in our focal laws and stuff to improve the imaging of this side surface so we can get good measurements. I can show the orientation of the probe on the C-scan down here. The north face is located at this position right here, so this is the back side of the bolt. You can see the indications on the back side of the bolt have higher amplitude than the ones on the front face, and that correlates well to what we saw visually. The corrosion was definitely worse on the back side. I positioned my probe at this point right here. And this is the point where I maximize the distance of our indications from the back side of the bolt in this, with the probe in this orientation right there. So then I move my measurement cursor over to that indication, and I measure across from the front face of the bolt out to that indication, and I get a measurement of 1.8 inches. And that actually was what we measured with the side scans. It didn't always work out that good on some of the bolts. A lot of times it was very cluttered on that S scan, and we couldn't really pick out what the surface was doing. But in this case, it worked out okay. Then I rotate my probe over to face close to the north face of the bolt, and got a pretty good indication there on the side, down about 10.5 inches. And if we look at it, I apologize for the quality of the picture. It was hard to get pictures of that stuff around there. You could hardly even fit the mirror in there, but you can tell that there's definitely something going on right in that location. I show this. This is a C-scan for 2 different scans on the same bolt. I just wanted to show how repeatable this method is. These 2 scans are pretty much identical. Even if we can't get measurements on the depth of corrosion, we can at least monitor these things because it is so repeatable. We could come back year after year and take scans and compare them to previous scans. So what did we find besides corrosion? This is bolt SE1. It's got a lot of stuff going on in the body of the bolt. I'm picking up stuff both with the positive and negative angles of the transducer. At this position, the probe is located right here on the back side of the bolt, and we got some indications look like they're pretty near surface. If I rotate the probe over to here, now we're looking at the side of the bolt, we get this big high amplitude indication internal to the bolt. And it looked to me like that indication on the surface on the back side was connected to that internal void in the middle. So I'm not sure what's going on there. Maybe there was a flaw internal on the bolt, and then the corrosion kind of worked its way in there. This is bolt SW6. You can see here that there's something big going on down at the bottom. This is actually below the visible area. This is down into just around the concrete interface area. And I've got a big indication about 180 degrees around the bolt, large amplitude, multifaceted. I can also pick it up with the negative side of the bolt over here. This one almost looks crack-like to me. This is probably the closest thing we saw that might be a crack. This is bolt NW2. This is, if you remember on the previous slide, this is the one that had the worst section loss according to the side scans. And I put the scanner on there and scanned it, and I get absolutely nothing in the C-scan. And I'm not sure what happened with that, except my guess is that something up top here is blocking the sound from getting down into the bolt. This slide shows this method that we're using the geometry of the bolt to measure, really depends on the top surface being perpendicular to the bolt. In this case, we didn't get that perpendicular, and you can see the wavy pattern in the C-scan down here. That's indicative of a wobble in the probe. So we can't really use that to make measurements to our corrosion, because our measurement cursors are vertical, but here the side of the bolt is not vertical. You can see the thread indications up here in the top of the bolt are not stacked vertically. I'm not sure what's going on in this bolt, but no, but seriously, the medical industry uses the same technology to look at humans, and I just wanted to throw that up there. So our conclusions. As far as the bolt scanning with encoded phased array, I thought it worked very well at detecting corrosion. It wasn't always good at measuring section loss, which was kind of our goal in this thing, but I think we do have room to improve that. Like I said, this is our first attempt at it, so repeatability was excellent. Even if we can't measure section loss, we can monitor, and documentation and reporting was very good. Northport status, there's an urgent repair design that's been complete. It's out for review right now, and very shortly we'll go to add and construction, and after which the restrictions can be lifted.